Subunit 6, Stoichiometry. Deduce mole ratios from balanced chemical equations. Solve mass-mass problems based on the given chemical equation. Define molar volume. State Avogadro's principle. Solve volume-volume problems based on the given chemical equations. Solve mass-volume problems based on given chemical equations. Define limiting and excess reactants. Determine limiting and excess reactants of a given chemical equation. Show that the amount of product formed in a chemical reaction is based on the limiting reactant. Define the term theoretical yield, actual yield, and percentage yield, and calculate the percentage yield of a chemical reaction from given information. Stoichiometry is the quantitative relationship between reactants and products in a balanced chemical equation. In other words, it's how we make sure that the mass is conserved on both sides of the equation. It obeys the law of conservation of mass. So the total mass of the reactants equals the total mass of the products. From a balanced chemical equation, it's possible to determine the number of moles of each reactant and product, the relative mass of each of the reactants and products. The stoichiometric coefficient tells us the relative number of moles of the substance that reacts or is produced. For example, nitrogen plus hydrogen yields 2 ammonia. So 1 mole of nitrogen reacts with 3 moles of hydrogen to give 2 moles of ammonia. So based on the chemical equations, we can calculate the mass-mass relationship, the volume-volume relationship, and the mass-volume relationship. 2 methods are commonly used in solving mass-mass problems. The mass ratio method. To do this, we write the balanced chemical equation. We write the known mass above the corresponding formula and X above the formula, the substance whose mass is to be calculated. Then we write the total molar mass, the molar mass of the substance multiplied by its coefficient, below the formula of each substance. Then we set up a proportion and solve for the unknown mass X. For example, what mass of oxygen is needed to oxidize 28 grams of iron completely? The atomic mass of iron is 56 grams. And oxygen is 16 grams. 4 iron plus 3 oxygen yields 2 iron oxide. 4 iron plus 3 oxygen yields 2 iron oxide. So we write the X above the oxygen, the 28 above the iron, on the bottom. Write the mass. Then we multiply them by the coefficient, so that's 4 for iron and 3 for oxygen. So the proportion is set up 28 divided by 224 equals X divided by 96. So we can solve for X and get 12 grams of oxygen needed. Then we can use the mole ratio method. First, you write out the balanced chemical equation. Then you convert the given mass into moles and place the mole and the required mass X above the formula. Write the coefficient as the number of moles under the formula. First, set up the proportion. Then solve for the unknown value and convert the moles obtained into mass. For example, how many grams of potassium chlorate are needed to produce 48 grams of oxygen? The moles of oxygen is equal to the given mass divided by the molar mass. You can tell this because the grams cancel out to yield moles. You get 1.5. So we put the 1.5 over the oxygen, the X over the potassium chlorate. We know there's 2 moles of potassium chlorate and 3 moles of oxygen. So 2 moles times 1.5 moles divided by 3 moles equals 1 mole of potassium chlorate. But now we can convert that to grams. The mass of potassium chlorate is equals to the moles that we just calculated times the molar mass. So the answer is 122.5 grams of potassium chlorate. The third way to do it is the volume-volume calculation. The volume of one of the reactants or products is given, and the volume of the other reactant or products is determined. We use Avogadro's law, which says that equal volumes of gases kept at the same pressure and temperature contain the same number of molecules. At standard temperature and pressure, STP, 1 mole of any gas occupies 22.4 liters. At STP, the temperature is 0 Celsius and pressure is 1 atmosphere. For example, how many liters of hydrogen are needed to produce 15 liters of ammonia by direct synthesis with nitrogen? First, we write the balanced chemical equation. Nitrogen plus hydrogen yields ammonia. Place the given volume and the required volume X above the formula. Then write the total molar volume below the formula. Set up the proportion. Now we can solve for X. X equals 22.5 liters of hydrogen is needed. For example, in a mass volume problem, how many liters of oxygen is required to react with 23 grams of methane? We set up the balanced equation, write the X above the thing we want to find out. We write the known grams of methane. Write the mass or volume, whichever is appropriate, on the bottom. And we set up the proportion. So 64.4 liters of oxygen is needed. Reactants are said to be in stoichiometric proportions when all the reactants are completely used up in a chemical reaction. But this isn't always the case. In many cases, an excess of one or more reactants is encountered. The limiting reactant is the reactant that is completely consumed in the reaction. For example, how many grams of hydrogen would be produced if 6.5 grams of zinc reacts with 5 grams of hydrochloric acid? First, write the balanced chemical equation. Then find out the moles of zinc. Then find out the moles of hydrochloric acid. Now calculate the number of moles in the product that would be formed by each reactant. First, we use the quantity of zinc. Now we want to know the quantity of the reactant of hydrogen. So we set up the proportion and we get 0.1 moles of hydrogen. We could also try by using the quantity of hydrochloric acid. We get 0.06 moles of hydrogen. That means the limiting reaction is the hydrochloric acid. That's because we make less hydrogen if we use this quantity. So the mass of hydrogen that's created is 0.12 grams. There are theoretical, actual, and percentage yields. Actual yield is the measured amount of product obtained in any chemical reaction. Theoretical yield is the calculated amount of product that would be obtained if the reaction proceeds completely. The percentage yield is the ratio of the actual yield of a real experiment to the theoretical yield multiplied by 100. So percentage equals actual yield divided by theoretical yield times 100. For example, if 99.8 grams of copper are heated in excess sulfur, 80 grams of copper sulfate is obtained. Calculate the percentage yield, noting that copper has an atomic mass of 64 and sulfur has an atomic mass of 32. First, we set up the proportion after writing the balanced chemical equation. We solve for x to get 124.75 grams of copper sulfate. So the theoretical yield is 124.75 grams, but the actual yield was 80 grams. So 80 grams divided by 124.75 grams times 100 equals 64.13%. So in summary, stoichiometry is the quantitative relationship between reactants and products. Mass-mass problems, mass-volume problems, and volume-volume problems are the main types of stoichiometric calculations. How many grams of calcium carbonate are needed to react with 15.2 grams of hydrochloric acid according to the following equation? First, we write x over what we want to know and the known value over hydrochloric acid. Then we write the molar mass underneath. Then we set up the proportion. X equals 20.8 grams. How many moles of water is required to produce 4.5 moles of nitric acid according to the following reaction? We set up the proportion based on the balanced chemical equation. Then we solve for x to get 2.25 moles. How many liters of ammonia is required to react with 145 liters of oxygen according to the following reaction? We set up the unknown and known on the top and the volume on the bottom. Then we can solve for x. 116 liters is required. How many moles of water vapor is formed when 10 liters of butane gas is burned in oxygen at standard temperature and pressure? Let's write the known and the unknown on the top, the moles on the bottom, times the weight, set up the proportion, and solve for x. 50 liters. If we want to get this into moles, 1 mole equals 22.4 liters. So 50 divided by 22.4 is 2.223 moles. How many liters of oxygen is required to react with 23 grams of methane according to the following equation? First we write the knowns and the unknowns. Then we write the weight and the volume. We set up the proportion and solve for x to get 64.4 liters of oxygen. Calculate the mass of calcium carbide that is needed to produce 100 cubic centimeters of acetylene according to the following equation. Let's put the knowns and the unknowns. But remember, 100 cubic centimeters is 0.1 liter. Then we write the weight and the volume. We set up the proportion, solve for x, and we get x equals 0.29 grams of calcium carbide. For the reaction, how many grams of hydrogen is produced if 0.8 moles of aluminum reacts with 1.0 moles of sulfuric acid? With the known and the unknown on the top, the mass on the bottom. Set up the proportion, solve for x. X equals 2.4 moles. If we use the other reactant, we see that the amount of hydrogen is 1 mole. Therefore, the limiting reactant is sulfuric acid. The mass of hydrogen created is 2 grams. When 20 grams of sulfur dioxide reacts with oxygen, 23 grams of sulfur trioxide is formed. What is the percentage yield? The actual yield is 23 grams of sulfuric trioxide rather. So 2 sulfuric dioxide plus oxygen yields 2 sulfur trioxide. First, we write the known and the unknown and the mass on the bottom. We set up the proportion and solve for x. 25 grams of sulfur trioxide. This is the theoretical yield, but what is the percentage yield? We have to divide 23 grams by 25 grams multiplied by 100 to get 92%. In this reaction, when 52.7 grams of octane burns in oxygen, the percentage yield of carbon dioxide is 82.5%. What is the actual yield in grams? We write the balanced chemical equation. We write the known and the unknown on the top, the weights on the bottom, set up the proportion, solve for x. 1 162.7 grams of carbon dioxide. This is the theoretical yield. So the percentage yield, which we know is 82.5%, equals the actual yield divided by this number. So the actual yield is 134.23 grams. Subunit 7. Oxidation and reduction reactions. By the end of this section, you will be able to define redox reactions, define the terms oxidation and reduction in terms of electron transfer, define oxidation number or oxidation state, state oxidation number rules, determine the oxidation number of an element in a given formula, describe the oxidizing and reducing agents. Analyze a given redox reaction by specifying the substance reduced and the substance oxidized, and also the oxidizing and reducing agents. And distinguish between redox and non-redox reactions. Oxidation is the process in which a substance loses electrons in a chemical reaction. Reduction is the process in which a substance gains electrons in a chemical reaction. Oxidation and reduction always occur together. So when one species is reduced, the other is oxidated, and vice versa. One example is sodium chloride. If you have 2 sodium and just chlorine, and they react together to form dissociated salt, sodium before the reaction has an oxidation number of 0, and after the reaction has an oxidation number of +1. That's because it has 1 fewer electron than it normally would. The chlorine has an oxidation number of 0. And then after the reaction, it has an oxidation number of -1. The sodium in this case has increased in oxidation number, which indicates that it has been oxidized. The chlorine has decreased in oxidation number, which indicates that it has been reduced. Said again, the sodium in this reaction has gone from neutral sodium to sodium plus, and it has lost 1 electron. This is called oxidation. Each sodium atom has lost 1 electron, which is turned into a sodium ion. In this reaction, the chlorine plus 2 electrons yields chloride ion. Each chlorine atom has gained an electron and changed to a chloride ion. There are rules for assigning oxidation numbers that will help you out a lot when doing these problems. First of all, the oxidation state of elements in a free state is 0. Calcium, sodium, oxygen, and chlorine in the last example. They will always have an oxidation state of 0. The oxidation number of a monoatomic ion is equal to its charge. So after the reaction, the sodium had a +1, which means its oxidation number was +1. The potassium here is +1, the magnesium here is +2, the oxygen here is -2. The oxidation number of oxygen in a compound is equal to -2. This will be very helpful to start you out when doing these problems. However, an exception is that peroxide is -1 and superoxide is -1/2. Oxygen difluoride is +2. Another rule is that the oxidation number of hydrogen in a compound is +1. In metal hydrides, like sodium hydride, calcium hydride, and aluminum hydride, the hydrogen has an oxidation number of -1. Another rule is the sum of all oxidation numbers of all the atoms in a neutral compound is 0. For example, we know that the hydrogen in a compound is +1. We know that the oxygen is -2. But since this compound does not have a charge, it all must equal 0. So hydrogen, there are 3 hydrogens, so 1 times 3 is +3. Let's go to the oxygen next. We know that it's -2, but there are 4 of them, so it's -8. We know that it has to equal 0. So that means phosphate has +5. Said again, in a polyatomic ion, the sum of the oxidation number of each element is equal to its charge. So here the carbonate is -2, so it all has to equal -2. We know the oxygen itself is -2, but there are 3 of them, so it's -6. Then you solve for the carbon and you know that it has to be +4. Another rule is that elements of the group 1A have +1 and group 2A have +2 oxidation states. In a compound, the more electronegative element is assigned a negative oxidation number and the lesser one is assigned a positive oxidation number. For example, the nitrogen has +3 and the chlorine has -1. What is the oxidation number of chromium in this compound? We know that it has to equal 0. So let's solve for X. Potassium is an alkyl metal, so said on the last slide, it has to be +1. We know that oxygen is -2. So we can solve for X. And we find that it has an oxidation number of +6. Example 2. What is the oxidation number of sulfur in this compound? The whole compound has a charge of -2, so the oxidation number of the whole compound has to be -2. We also know that the oxidation number of a single oxygen is -2. Let's solve for X.